Hello everyone and welcome back to my channel. This is the A+ Tutor. Today I'd like to give you an introduction to limits. So what is a limit? The limit of a function is the value of that function as it approaches a specific x. So typically you'll see problems like this, and the way that we read this is the limit as x approaches 1 of x squared minus 1 over x minus 1. The question we're asking is, what is the limit of the function as x approaches 1? So let's try something out here. And let's see what happens when you plug in 1. Well, the limit as x approaches 1 of 1 squared minus 1 over 1 minus 1 would be 0 over 0. So is this equal to 0? Well, the limit of this function is not 0. So instead, let's consider the values of this function as x approaches 1. Now, if we look at a number line, x can approach 1 from two different ways. Either from the left, where we have 0.5, 0.75, 0.9, and we keep getting closer, 0.99, 0.999. And then we have from the right, where we're at 1.5, 1.25, 1.1, 1.01, 1.001, and we get closer. So we want to consider what this function is doing as we're approaching 1 from both sides of that 1, from the left side and from the right side. All right, so let's start at 0.9. When we plug that in, we get negative 0.19 over negative 0.1, which is equal to 1.9. Let's go just slightly closer, 0.99. And of course, you may need a calculator to solve these. But this gives us negative 0.0199 over negative 0.01, which is equal to 1.99. Let's look at one more, 0.999. Plugging this in gives us 1.999, and as we can see, as we continue to get closer to 1, all of these values are getting closer to 2. Now let's look at what happens when we approach 1 from the right side. So from the right side, let's start at 1.1. When we plug in 1.1, we see this is equal to 2.1. So let's get a little bit closer. We have 1.01. When we plug in 1.01, we get 2.01. And let's look at one more at 1.001. And this is equal to 2.001. So we can see these are also getting closer and closer to 2. This means the value of our limit is actually 2. So when we do solve these limits algebraically, or like this when we're plugging in points, we can't always trust just plugging in the value of the limit, because in this case, it did not give us what the limit was. It gave us 0, when in reality, our limit of this function is 2. If we look at our original function, we can rewrite this as x plus 1 times x minus 1 all over x minus 1, and those x minus 1's can cancel. So in reality, we're taking the limit as x goes to 1 of just x plus 1, and when we plug in 1, we get 1 plus 1, which equals 2. So sometimes we may need to simplify our functions in order to solve limits, but this is a really great example to show you that you cannot take things exactly as you see them. Just plugging in 1 gives you 0, which is not your limit. You always want to make sure you're evaluating and finding the correct value. And sometimes we can't even simplify our functions. We just have to use the values as we approach the limit, that x value for a limit. We just have to use those values in order to figure out what the limit of the function is. Now, let's consider the following graph. And we want to evaluate the limit of f of x as x approaches 2. So here we don't know what the function for f of x is. We don't know what the actual equation is. So we have to rely on the graph in order to solve this limit. This means we need to consider the value of the function as x approaches 2 from the right and from the left. From the left would be this way, and from the right would be this way. Basically, the way that we can express this is we can write these individual limits as the limit as x approaches 2 from the left with a little minus sign of f of x, or the limit as x approaches 2 from the right with a little plus sign of f of x. Basically, are we coming from the positive direction, which would be the right, or from the negative direction, which would be the left? So anytime you see a little minus or a plus to the right of that value for your limit, that tells you that you're looking for a one-sided limit. What we're doing is we are approaching 2 from either the left or the right. So when we approach 2 from the left, we're looking at from the negative side. As we approach 2, the value that we have is 4. So the limit as f of x approaches 2 from the left is equal to 4. And then as we approach 2 from the right, the value of the function is 2. So that means the limit of f of x as x approaches 2 from the right is equal to 2. So the limit of the function as a whole does not exist because the limit as x approaches 2 from the left is not equal to the limit as x approaches 2 from the right. Now, if these were both equal to 2 or to 4, then the limit of f of x would be 2 or 4, whatever they were both equal to. But since they're not equal, this limit does not exist. In general, there are two ways that we can evaluate limits, either graphically or algebraically. So let's look at some examples of evaluating limits graphically. Now this may look like a lot, but let's work through each of these, and each row, they all actually have to do with each other. First of all, we're given a graph and we're given a set of limits that we want to evaluate. So if we look at this graph, there are different areas where we have holes in our graph. This is where the value of that function does not exist. We also have some jumps and we have some points. So now we want to evaluate all of these limits based on the graph that is given to us. So let's start with the first one. We have the limit as x approaches -3 from the left of f of x. Here's our -3 value. As we approach -3 from the left, so from the negative side, the limit of that function is +1. The value of the function does not have to exist at that point. We just want to see what that function is getting close to, and that is +1. Now let's look at the limit of f of x as x approaches -3 from the right. So we want to see what the value of this function is as we approach -3 from the positive side or from the right side. So as we get closer to -3, the value of our graph is again 1. Since these two values are equivalent, since they are the same value, we know that the limit as x approaches -3 of f of x is 1. But the value of the function f of -3 does not exist. And why is that? Because there's a hole where the y value of -3 should be. There is no value there, therefore the value at -3 does not exist, but the limit of the function as x approaches -3 is 1. Now let's look at our next set. We have the limit of f of x as x approaches -1 from the left. So now we're approaching -1. As we approach -1 from the left, we're coming to this point. If we follow the graph from the left, it's coming down to this point at -2. Now, let's approach -1 from the right. As we approach -1 from the right, we're coming up to this point up here at f of x equals 3. Now, we want to find the limit of f of x as x approaches -1. Since our two limits from the left and the right are not equal, this limit does not exist. Now let's see if we can find the value of f of x at x equals -1. So f of -1 is going to be equal to -2 because we have a solid point at -2, which means that point exists. Let's look at our next set. We have the limit of f of x as x approaches +2 from the left. As we approach 2 from the left, we follow this graph. We're approaching this point up here, which is +2. Now we want to find the limit of f of x as x approaches 2 from the right. So if we trace our graph from the right or come from our positive direction, we're coming to this point here, which is +1. Again, since our limit from the left and from the right are not equal, the limit of f of x as x approaches 2 does not exist. Last, we have the value of f of x at x equals 2, or f of 2, which is going to be +1 because we have a solid dot where the value at 2 is for the y value of 1. Wherever we have that solid point means that value exists, so f of 2 is 1. Now let's take our last set. So we want to find the limit of f of x as x approaches 6 from the left. So as we approach 6 from the left, we're brought to this point, which is 1. Now we want to find the limit of f of x as x approaches 6 from the right. From the right, we're also brought to that same point, which is 1. This means that the limit of f of x as x approaches 6 is 1, but the value of f of x at 6 is 3. This is because we have a hole at the y value of 1 on this section of the graph, and our point is actually up at 3. But the limit as we approach that point is 1. So this is how we would solve our limits graphically. We would use the traits of the graph in order to determine what our limits are. Now that we saw how to evaluate limits graphically, let's work through evaluating limits algebraically. When we evaluate limits algebraically, we'll typically just plug in and solve. The only time we won't plug in is if we need to simplify our function, but for the most part, we'll be able to just plug it in and solve for the value of that limit. To evaluate this limit, we want to plug in the value, in this case, which is 2, and solve. So this becomes 2 squared minus 2 plus 1, which is 4 minus 2 plus 1, or 3. So that means the limit as x approaches 2 of x squared minus x plus 1 is equal to 3. Let's look at the graph of this function to confirm that we found the correct limit. So we're evaluating the limit as x approaches 2. As we approach 2 from the left, we get 3. And as we approach 2 from the right, we also get 3, which means the limit that we evaluated is correct, and the limit of this function as x approaches 2 is 3. Next, we have the limit as x approaches 1 of 2x plus 1 over 3x minus 2. Again, we're going to plug in 1 and solve. So this becomes 2 times 1 plus 1 over 3 times 1 minus 2, which is 2 plus 1 over 3 minus 2. This is equal to 3 over 1, or 3. That means the limit as x approaches 1 of 2x plus 1 over 3x minus 2 is equal to 3. Now let's use the graph to confirm. So we're evaluating this limit at x equals 1. So here's where x is equal to 1. As x approaches 1 from the left, we get to 3. As x approaches 1 from the right, we also get to 3, which means our limit is correct. Now, let's consider the limit as x approaches 1 of the square root of 10x minus 1. To evaluate, we're going to plug in 1 and solve. So, we'll plug in 1, which gives us the square root of 10 times 1 minus 1, which is the square root of 10 minus 1, square root of 9, which is equal to 3. So the limit as x approaches 1 of the square root of 10x minus 1 is equal to 3. Let's consider the graph of this function to confirm. So as x approaches 1, which is here, as we approach 1 from the left, we're approaching the value 3. And as we approach 1 from the right, we're also going to 3, which means our limit is correct. And finally, let's look at the limit as x approaches 2 of x squared minus x minus 2 over x minus 2. Now typically we would plug in 2 and solve. But when we do this, we would get 2 squared minus 2 minus 2 over 2 minus 2, which is equal to 4 minus 4 over 0, or 0 over 0. So this is unlikely the value for our limit, which means first we actually want to simplify our expression, then plug in 2 and solve. So x squared minus x minus 2 over x minus 2. If we factor our numerator, we'll get x minus 2 times x plus 1 in our numerator, and our denominator is x minus 2. So we can simplify that by canceling this x minus 2, meaning we're just finding the limit of x plus 1. So our new limit becomes the limit as x approaches 2 of x plus 1, which is equal to 2 plus 1, or 3. Now let's consider this graph to confirm. So now we are looking at the function as x approaches 2, or 2 is right here. So as we approach 2 from the left, we are approaching the value 3. And as we approach 2 from the right, we're also approaching the value 3, which means our limit is correct. Let's take one more example of evaluating limits algebraically, but this time with a piecewise function. A piecewise function is similar to the graph of the set of functions that we saw when we were evaluating limits graphically. This is just a version of a piecewise function written algebraically. And we want to solve limits based on this information. Now, although this looks like a lot of problems for this piecewise function, when we get into it, you'll see it's pretty straightforward. So let's start with our first set here. We have the limit of f of x as x approaches 1 from the right. So when we're looking at the value that x is approaching, that's what we're going to use to determine which one of these functions we need to use to evaluate the limit. As x approaches 1 from the right, that means x is less than 2, so we're going to use this first function here. So we're going to say, okay, the limit as x approaches 1 from the right of x plus 1. So now when we plug that in, we get 1 plus 1, which is equal to 2. Now we have the same thing, except from the left. The limit of f of x as x approaches 1 from the left. So again, from the right or from the left, we're still in this first function. So we can write this as the limit as x approaches 1 from the left of x plus 1, which is equal to 1 plus 1, which is 2. Now when we're looking at the limit of f of x as x approaches 1, we know two things. One, we know that this is going to be the limit as x approaches 1 of x plus 1, and since our limits from the left and right are equal, we know that this is going to be equal to 2. And finally, f of 1, again, 1 is inside that x is less than 2 value, which means f of 1 is equal to 2. Next, we have the limit of f of x as x approaches 2 from the right. So when we think about our number line, 2 from the right means we're getting bigger to smaller. So we're going from 3 down to 2, which means our 2 from the right will be inside this second function. So the limit of f of x is going to become the limit of x squared minus 2 as x approaches 2 from the right, which is going to be equal to 2 squared minus 2, or 4 minus 2, which is equal to 2. Now when we look at the limit of f of x as x approaches 2 from the left we're going from 1 to 2. Well, 1 exists within our first function. That means we have to use this to find the limit as f of x approaches 2 from the left. So this becomes the limit as x approaches 2 from the left of x plus 1. So this is 2 plus 1, which is equal to 3. Next, we have the limit as x approaches 2. Well, 2 does not exist in this graph. We actually don't have a value for 2. And when we approach 2 from the left and from the right, these values do not match. So that means this limit does not exist. And last, f of 2, again, we don't have a value for 2 in this graph. Our x values do not include 2, which means the value at f of 2 also does not exist. Now let's look at our last section. We have the limit of f of x as x approaches 4 from the right. Let's look at another number line. So from the right, we're approaching from 5, which means anything greater than 4. This is what we're going to use when we're approaching 4 from the right. So this becomes the limit as x approaches 4 from the right of the square root of x plus 5. This is going to be equal to the square root of 4 plus 5, or the square root of 9, which is equal to 3. Next, we have the limit of f of x as x approaches 4 from the left. When we go from the left, let's say we're going from a value like 3, which means we're going to fit in this set up here, and our limit will become the limit as x approaches 4 from the left of x squared minus 2. So this is going to be equal to 4 squared minus 2, or 16 minus 2, which is equal to 14. So for our limit as x approaches 4, the value of the limit as x approaches 4 from the right and from the left do not match. Therefore, this limit does not exist. But the value for f of 4 does exist because we do have x is greater than or equal to 4. So this is going to be equal to the square root of 4 plus 5, which is equal to the square root of 9, which is 3. Thank you so much for watching. I hope you enjoyed and I hope you learned something. If you enjoyed this video, give it a thumbs up. If there's something else you'd like for me to review, leave a comment down below and I'll be sure to get to it. I upload new videos every week, so make sure you're subscribed so that you don't miss another video. You can also find me on Instagram and on Facebook at the A+ Tutor. See you next time.